Great, welcome back everybody. I think we'll make a start. This first session this morning is a collection of observations sort of gathered over me watching people learn OpenMP and use OpenMP over quite a few years now, to just point out some of the pitfalls that are easy to fall into, and also things that you can do to make your life easier as an OpenMP programmer, and things to watch out for. Okay, so these are in no special order, but start off with directives. So one of the problems with this mechanism for OpenMP of using directives is that if you mistype the sentinel, then you may be unlucky and the compiler might not raise any error message. So if you miss out the $, for example, from $OMP, or you mistype the pragma name in C and C++, then the compiler is entirely entitled just to ignore that line of code and not tell you about it. My experience, Fortran compilers are really bad, or just don't, because they just see that as a comment. Some C++ compilers will tell you that that's an unrecognized pragma, but not all of them. So you have to be really careful with this, and it's, sometimes it's kind of annoying but harmless in the sense that you will just not get any parallelism, and you will go around scratching your head for a while wondering why you've implemented OpenMP and you're not seeing any difference in performance whatsoever. But there's even nastier cases. Okay, so if you do this with some synchronization constructs like atomic, then you can accidentally have a race condition that you thought you'd solved. What can you do about this apart from being careful? If you know that you're prone to certain typos, you could write a script to search for them, or you could do something, you could do something a bit more sophisticated. You could write a script to look for things like, strings like OMP inside a Fortran comment, or pragmas that aren't OpenMP or something like that. You could do something like that. Say, probably not really worth it for small projects, but if you're doing if it's a large application code and you're doing continuous integration or something like that, then that's something you could build in as a test into your CI process. Okay, so we talked a bit about the mechanism that the directives are designed the way they are, and to help you try to write code that works without OpenMP as well as with OpenMP. And extra feature which I didn't mention is that if you need to do if-defs rather than just ignore directives, then the macro _OpenMP will be defined if the code is compiled with the OpenMP switch in the compiler. Okay, so the name of that macro is part of the standard, and is the same across all compilers. So if you compile with the OpenMP switch on your compiler, then _OpenMP is defined, and so you can do you can do if-def _OpenMP type macros. Of course, you don't have to use that. You can entirely build your own macro system for and conditional compilation system. So again, some applications have their preferred methods and styles of doing this. Okay. So next one is, well, we're starting to stray here actually a little bit into performance issues, which I'm going to cover in a lot more detail in the second session today. But so important thing is to realize that parallel regions come with some overhead, and the overhead of executing a parallel region, just to give you an order of magnitude, is that typically in a few tens of microseconds. So obviously that will depend on things like the compiler that you're using, it'll depend on the hardware that you're running on, depend on the number of threads. So the overhead typically increases with the number of threads. So that's the kind of time that you have to be aware of, in the sense that the sequential execution time of a section of code has to be several times that overhead in order to make it worth parallelizing. So you might have a situation in your code where you execute a parallel region lots of times, but some values, like for example, might be just like the number of loop iterations, might vary from one instance to another in the code. So it's you've got a single instance in the code, but that gets executed lots of different times, and sometimes it has a lot of work in it and sometimes it doesn't. So if you're in that situation, then what you can do is the parallel directive takes an if clause, and so that can decide at runtime whether to go parallel or not. So you can, that's a convenient way of deciding, okay, based on some condition which you put in the if clause, to decide whether there's sufficient work or execution time in the block of code to make it worth going parallel. So there is still some overhead of executing a parallel region on a single thread. It's not completely nothing, but it's typically a lot smaller. So much less than typically a lot less than a microsecond, something down to the order of tenths of a microsecond. So it's one or two orders of magnitude smaller overhead if you only have a single thread. Okay. So next one is to do with loops and when it's safe to use a no wait directive. So the issue here, so the problem here I'm thinking about is that I have two loops here. Let me get a pointer. Okay, so the first loop writes some values into an array A, and the second loop is going to read them. Okay, so the question is it safe to remove the barrier synchronization at the end of the first loop using a no wait clause? And the answer is yes, provided a couple of conditions are met. Okay, so provided the number of iterations is the same, okay, and they are in this case, the loop bounds are the same here, and the schedule is static, with or without a chunk size, then it's safe, because then you are guaranteed that these two loops will have the same mapping of iterations to threads. So that means you are guaranteed that the thread that writes AI in the first loop will be the same thread that reads it in the second loop, and therefore it is safe it's free from race conditions to suppress the barrier at the end of the first loop. Okay, more about loops. So if we have a loop which has bad load balance, then one of the tools we have is choosing a loop schedule. So typically either static or dynamic, and specifying a chunk size. And typically do some experiments to try and determine a good chunk size. The problem is that tuning the chunk size can be quite tricky because the optimal chunk size can depend quite strongly on the number of threads. And we're typically interested in writing code which does not specify the number of threads or is not dependent on the number of threads. So one possible way around this is that it's often more robust. Is what you actually tune is not the chunk size itself, but the number of chunks per thread. Okay, and you can do this quite conveniently because the chunk size expression doesn't have to be a compile time constant. It can be calculated at runtime. Okay. So what you can set is a value, say, so C per T here is going to be the number of chunks that each thread is going to execute. Okay, so then from that, and if you know that you can get the number of threads that are going to execute, and you can then sort of from the number of loop iterations, the number of chunks per thread, and the number of threads that you've got, you can then use an expression like this to calculate the chunk size at runtime, which will be different depending on the number of threads that are executing. Okay, and it turns out that that's a more robust thing to tune. Okay, so the optimal value is more like of the number of chunks per thread is less likely to be sensitive to the number of threads than the chunk size itself. Okay, any questions so far? Okay, so next one is, should I use single or master? Okay, because they have quite similar functionality in that, both of these constructs will cause a code block to be executed by one thread only, while the others skip it. So which one should you use? Okay. Well, a couple of considerations here. Master has lower overhead because it's really just a test. Master is just convenient syntax for if my thread ID equals 0 or not, and that's so it's very simple and easy to implement. Whereas single requires some synchronization because the runtime has to take care of the case where multiple threads might reach the single at the same time, so they have to agree amongst themselves which one is going to execute the single and which ones are not, all the others are going to skip it. So that requires some internal synchronization and more bookkeeping. As I said, but as we looked at before, be aware that single has an implied barrier, but master doesn't. So if you need synchronization at the end of the block, then you might need to add an explicit barrier if you use master. On the other hand, if you have some good reason to expect some threads to arrive before others at this block, then it might make sense to use single, okay? Because then the first thread that gets there that execute it, they don't have to wait for thread 0 to arrive. Okay. Let's move on to data sharing attributes. Okay, so yeah, Don't forget, private variables are uninitialized on entry to parallel regions. That's quite a common source of bugs. So you obviously you can use first private, but it's more likely just to be a mistake because, as I said before, the use cases for first private are actually surprisingly rare. You think it's going, when you first see it in OpenMP, you think, oh, that's going to be a really handy feature. But in practice, it's very rare to require it. So as I said, you should, if for variables which are read-only inside the parallel region, it's almost always absolutely fine to just keep them as shared. That doesn't have any performance consequences typically. Whereas first private, there is some overhead to create well, probably not to create the copies really, but to actually copy the values. There can be some overhead involved in doing that. Okay, I'm going to repeat this one again because I think it's really important, and I just want to strongly encourage you down this route. Okay, and that's using default none. So because the default behavior for parallel regions and work sharing constructs effectively is the same as default shared. Okay, so if you don't specify any default clauses, then what you get is variables are shared by default. And that turns out to be extremely dangerous. It makes it far too easy to accidentally share variables. And as I said, it's probably, I think if look back at the design of OpenMP, that this is the one big bad decision, or the worst decision that was made. Okay. So I would say, okay, right. Always use default none, and I mean always. Just get yourself into the habit of it. So for Fortran programmers, it's the same. It's the kind of the same deal as using implicit none. Okay, it's just something that you should automatically do, and not question it, and not not think about trying to save yourself typing. Why is this so important? It's because everybody suffers from, or almost everybody seems to suffer from, what I call variable blindness. So if you ask people to list all the variables that are accessed in a block of code, then people will almost inevitably miss some of them. So it's things like things that are accessed inside that are just accessed inside if tests, or things that appear as loop bounds. So variables like that are very easy to miss, and the consequences of screwing up are just so bad. And I would strongly encourage you to always use default none, even though it's going to mean some extra work and some extra typing. It's going to be worth it in the long run. Okay. So and another reason is that if you make a mistake with accidentally sharing variables, it may never show up unless you do something, until you port the code to another compiler or change the flags or something like that. Okay. So here's a piece of code with a bug. Okay, and the bug is fairly, in this case, it's reasonably obvious. Okay, it's that this variable temp is shared by default here. Okay, because there's nothing, there's no default or shared or private clauses on the the parallel region. Okay, so everything will be shared. So everything that's not declared inside the parallel region. So I and J will be private because they're declared inside, but N and M and B and C and A and D and temp will all be shared. Okay, and so sharing temp causes a race condition, because you're going to get multiple threads trying to read and write it at the same time. What's the problem here? Okay, so the problem is particularly nasty because if you compile this code with sufficient optimization, then the value of temp will never actually be stored in memory. Okay, the compiler will optimize those loads and stores away, and temp, the value of temp, will only ever be stored in registers. So kind of what the optimizing compiler is doing is, or the side effect of the optimizing compiler is to accidentally privatize temp for you. Okay, because every thread is going to have it's actually going to have its own copy of this value in a register. But so you might always, you might never see the bug, you may not never observe the consequences of the bug until you say, until you give your code to somebody else and they decide to build it without compiler optimization, and then suddenly they get the wrong answer. So as I say, it's race conditions are really, really nasty sorts of bugs. There are some tools which I will mention later on, which you can use to detect them. So it's not a completely hopeless story, but it's still, nevertheless, it still pays to be extremely defensive in our software engineering practices to try and do everything we can to avoid having race conditions. Okay, next up, this is kind of a slightly obscure one, but this is to do with the interaction between private clauses and global variables. So the problem would occur here is, okay, suppose I have some global variable foo, which is declared at file scope here. And then I have a parallel region which accesses foo, and I decide that I want every thread to have its own copy of foo, so I declare it in a private clause on the parallel region. Okay. So that's fine on its own, but then what happens if inside the parallel region I call a function, and inside the function there's also an access to foo? Okay, so for example, through an extern statement, this function can also reference the same global variable. And the answer, so the problem is that what does this refer to? When we access foo inside the function, does this refer to the original storage of the global variable, or does it refer to the private copy in the parallel region which calls this function? And unfortunately, the answer is it could be either. So the OpenMP specification says you don't know what's going to happen here. Okay, so that's kind of unpleasant, and it basically means that you can't use this kind of pattern because it'll, the behavior will change from one compiler to another. So if you really want to access the private copy, then you would need to pass it through the argument list. Okay, so if you passed foo through as an argument to some func and then reference that inside, then that would be okay. Or if your code is more complicated and that doesn't seem like a feasible option, then that might be an instance where you might need to use thread private rather than declaring it on a private clause. you might wonder, why does that happen? Well, why is there any ambiguity here? The problem is that what is to do with compiler inlining. Okay, so inlining is compiler optimization, where the compiler will replace the call to some func by the body. Okay, so it'll basically eliminate the function call by hoisting the body into here. And so if it does that, then it basically would be natural for foo to refer to the private copy. So it's basically saying, okay, inlining may or may not happen, and the compiler can't really deal with trying to figure out whether inlining is safe or not, and guard against this kind of problem. So, and it's just it's a problem that the compiler just can't really deal with. Okay. So this next one is usually a problem for more for Fortran than for C and C++ typically, and so hopefully we're seeing less. You know, old Fortran codes like this are dying off slowly. Okay, but you might get unlucky. You know, somebody might ask you to, might give you some horrible old piece of Fortran and say, please, can you add OpenMP to this? Okay, and then you look at it and you see, what do you see? Okay, you see, you see a loops, and these are, the body of the loop consists of, several pages of code and references, hundreds of different variables. So then you say, okay, okay, if I'm going to parallelize this loop with OpenMP, then I need to determine the correct scope, whether all those variables need to be private or shared or reduction, and that's that's tedious and error prone and difficult to test easily. So what can you do? Okay, so in this situation, it would be useful to refactor the code so that instead of having inline code, you put that big block of code inside a subroutine. Okay, so you refactor your sequential code so that it looks like this, and then you can make all the loop temporary variables can be declared locally inside this routine. Okay, so, and that means that they will be automatically privatized when it comes to running to adding OpenMP, and then past the rest, shared and reduction variables get passed through the argument list. So that's just this step is then just becomes a sequential refactoring step. So that's much easier to test whether you've got it right or not. And then you can attack the parallelization afterwards, and hopefully that will reduce the number. You've already sort of had to think about which variables you need to might potentially be shared, so the ones that you can't make temporaries, and then think about parallelizing them. Okay, so you already had to think about it, and but you've done it in a sequential code context, which is much easier to test adequately. This is not really a big problem for C and C++. Typically, you don't tend to see this horrible kind of pattern, and you can just declare temporaries in the scope of the loop body anyway. Okay, so this is a nasty one, and this does actually crop up in one of the exercises. So this is a situation where we have a parallel region, and we have a parallel loop inside the parallel region, so a work sharing loop inside the parallel region with a reduction on it. Okay. and I want to do it like this. I want the reduction on the loop here rather than on the parallel region, because I need the result of the reduction later on inside the parallel region. Okay, so I'm going to set sum equal to 0, then have a parallel loop, which is a reduction pattern on sum, and then I want to use the result of that reduction somewhere later in the parallel region. Okay. So, well, what do I have to do? Well, in order for this to work, I have to declare sum has to be shared with respect to the parallel region. Okay, so you cannot do a reduction on a private variable with respect to a variable which is private with respect to the parallel region. And that kind of makes sense, because if you think about it, because then it's not clear, you've got which is the original. What does that mean? What's the original copy? What's the original value? Well, what's the initial value? Well, it could be, is it the sum of the values on all the threads, or the value on thread 0, or what? Okay, it doesn't really make a lot of sense. So you can't, and you're not allowed to do it. So sum has to be shared parallel region, but then I need to initialize sum somewhere. Okay, and well, this is wrong for two reasons. One of them is probably harmless, but the second one isn't. Okay, so the first reason this is incorrect is that, okay, this statement here, setting sum equals 0, is going to be executed by every thread. So technically speaking, that is a race condition. Okay, you're not supposed to do that. But having every thread write the same value to a variable isn't probably going to cause any problems. So it's technically incorrect as far as OpenMP specification is concerned, but it's probably not going to have any bad consequences. What does have bad consequences here is that there is also a race between this initialization, and there's an implicit write that's going to happen to this shared variable to form the reduction at the end of the work sharing loop. Okay, so a reduction like this comes along with an implicit write to that storage, and we have to be careful to synchronize those correctly. And in this case, they aren't. Okay, so what could potentially happen here, and whether it does or not depends a bit on the how the reductions are actually implemented. But what can potentially happen here is that one thread starts executing here. It sets sum equal to 0. It goes into the loop. It does all its loop iterations. It adds its partial sum into the original storage for sum. And then some other thread comes along later and resets sum back to 0 again. So the consequences of that are, yes, bad. Okay, so it would be possible to for sometimes, okay, for this to get the wrong answer, because one or more of the partial sums might get overwritten. Okay, so what can you do? Okay, well, in this case, there's a simple answer, which would be to move the initialization outside the parallel region. But that's not always possible. There might be an example. So there might be another sequential loop surrounding this. Okay, so you might want to have to keep resetting sum to 0. So you have to synchronize this correctly. Okay, so putting it in a single region, for example, would be an acceptable solution, so that only one thread does the initialization, and all the other threads have to wait for the initialization to happen before they start executing the loop. Okay, next problem. So this is particularly confusing. Okay, so what you might do is say, okay, I'm about to develop some. I've got an existing code. I want to add OpenMP to it. The first thing I'm going to do is I'm just going to change my build procedure to add the OpenMP flags to the compiler. Okay, so I'm not going to touch the code. I'm just going to get my build process and compiler flags sorted out first. Okay, and then you go ahead, you compile the sequential code with the OpenMP flag set, and suddenly your code stops working. You think, okay, what on earth happened there? Well, a couple of things might have happened. Okay, one of the things that could happen is that you have a bug in your code, which is assuming that the contents of a local variable are preserved between function calls. Okay, so in other words, you're missing a for Fortran a save, or for C and C++ a static. Okay, so what changes when you compile with OpenMP? Well, compiling with OpenMP set forces all local variables to be stack allocated and not heap allocated. Okay, so typically the compiler actually has a choice, okay, to decide, for sequential code, it can decide whether to put local variables on the stack or on the heap, and it doesn't matter very much what it decides to do as far as we're concerned as programmers. We can't really tell the difference. However, because of OpenMP's privatization rules, okay, so in that local variables, if we call a routine or a function inside a parallel region, local variables must be private by default. So the way the compiler has to handle that is to force all those local variables to be stack allocated, because the compiler, and do it for the whole code, because the compiler cannot tell which functions are going to be called from inside parallel regions and which are not. Okay, so it can't, the compiler can't do this selectively. It has to apply it across the entire code. So the other consequences of that you might see is that you get stack overflow. You run out of stack space, particularly if you have local arrays of any reasonable size. Then, and typically the default stack size for OpenMP threads is not that big, so a few megabytes would be typical. You can easily run into stack overflow problems. So your code dies horribly with a segfault because you ran out of stack space. Okay, so if it's a bug, then you need to use save or static correctly, clearly. But that's that might cause you further problems, because then those things are then you're then forcing those onto to be heap allocated, so then they're shared by default. So that might also cause you some problems. Okay. So one common pattern which uses save or static is first time through code. Okay. So you have a flag which is initialized, and the first time a function is executed, you conditionally execute a block of code based on the value of the flag, and then you toggle the flag, and then all subsequent executions of the functions don't execute that code block. Okay, so that's it's a common pattern. It's not a very nice pattern, but it's one that you probably come across. So then you think, okay, well, if that first time through code, if that's going to happen inside a parallel region, what am I going to do? Okay, how can I handle that? Synchronize it correctly, or maybe refactor your code so that you do that once explicitly outside before you get to any parallel regions or anything like that. So dealing with that pattern can take a bit of thought and a bit of refactoring. Okay, so yeah, if you run out of stack size, then then there are things you can do to deal with that, but it's slightly messy. So if you have, particularly if you have large private data structures, then it's possible to run out of stack space. So the way this works in OpenMP is it's slightly messy, because the size of the thread stack apart from the master thread can be controlled by an environment variable. So you can set OMP_stack size before you execute the program, and that will set the amount of stack that every thread apart from the master thread has. Okay. The size, on the other hand, the size of the master thread stack is controlled in the same way as you would for a sequential program. So that could either be via a compiler switch or using a Linux command like ulimit to set the amount of stack space for the process. Why this messy thing? Well, the problem is that as far as the master thread is concerned, OpenMP typically is unable to control that, because by the time the OpenMP runtime gets invoked, that initial thread is basically the initial thread in the process. That thing's already been created by the operating system with a given stack size, and so by the time OpenMP gets involved at all, it's too late. Okay, it's not able to change the size of the stack for the existing thread. So if you do run out of stack size, you typically have to do both these things to get enough stack space on all the threads. Okay, next one is to do with synchronization. I did mention this before, but just to reiterate, okay, you can't mix critical and atomic to protect the same shared variables. Okay, so if you try to do that, then they don't mutually exclude. Okay, so I say one way of thinking about this is, which is helpful, is that critical really protects access to code, and therefore by sort of access to memory locations implicitly, whereas atomic directly protects access to individual memory locations. So if you wrote something like this, okay, a parallel region where you have an increment to A that's inside a critical section in one place and as an atomic in another, you still have a race here, because it's possible for one thread to, it's still possible for a thread to be executing A plus equals 2 at the same time as another thread is executing A plus equals 3. Okay, next one is allocating storage based on the number of threads. Okay, so again, this is a problem if you want to write code which is number of thread agnostic, so it will work for any number of threads. Sometimes you want to be able to allocate some storage whose size is determined by the number of threads. You want a piece of shared, maybe a piece of shared memory, but the size of that is going to be some multiple of the number of threads. And the question is, how do you know how many threads the next parallel region is going to use? If we're inside the sequential part of the program, calling OMP get num threads is going to return 1. Okay, so that's no use. However, there is a different function that you can call, which does return what you want, and this is called OMP get max threads. Okay, and what that actually does is, talked about internal control variables before. Okay, what this does is actually return the value of the internal control variable for the calling thread, which determines, well, at least an upper bound on the number of threads that will be used by the next parallel region that this thread creates. Okay, so this this works provided we don't use a num threads clause on the parallel region, because the num threads clause will override this value. Okay, so if you want to allocate some storage up front based on the number of threads that are going to be used in the next parallel region, then you can call OMP get max threads. Okay. So again, unfortunate choice of terminology. This happened in OpenMP because the notion of internal control variables wasn't in there from the start. Okay, it was something that was added in a subsequent version change. There's an internal this internal control variable. So OMP set num threads sets that internal control variable. OMP get num threads does not return its value. Okay. The getter function is get max threads, not get num threads. So that's kind of ugly and unfortunate. Okay, it's important to note that there are the OpenMP specification has quite a involved algorithm in it, which tells you how many threads you're going to get for any parallel region. But there's always a get out. Okay, no matter what you specify, there is always a possibility that implementation will deliver you fewer threads than what you asked for. Okay, so if you want to write robust code and be defensive against potential bugs, if your code depends on there actually being a certain number of threads, then you should always call OMP get num threads inside the parallel region to check that you've got the number of threads that you were asking for. Okay, because there are always circumstances in which the implementation is allowed to deliver you fewer than what you asked. Okay. So there are also some environment variables which can affect performance. And depending on different implementations have different defaults for this. Okay, so it's worth knowing about them and things that you might need to set depending on the system. Okay, this is usually not such a problem for HPC systems with batch systems. Okay, so if you're running on something like ARCHER2 where you're launching jobs with Slurm, then you have exclusive use of nodes, then these kind of issues don't really arise. The default behavior is usually absolutely fine. Okay, but more generally, then you can't necessarily rely on the implementation doing what you want. Okay, so what things can you do to try and maximize the performance in terms of what the OpenMP runtime is doing? Okay, you can set OMP wait policy to active. What that does is that encourages idle threads to spin and consume CPU cycles rather than go to sleep. Okay, it doesn't prescriptively determine the behavior. It doesn't guarantee that they're going to spin forever, but it's a hint to the OpenMP runtime that you'd rather your threads were spinning between parallel regions and are quick to reactivate them rather than putting them to sleep and releasing the CPU resources. Second one is so related to the last point I was making is OMP dynamic equals false. So this is nothing to do with the schedule kind, which is called dynamic. Okay, so again, another unfortunate piece of nomenclature in OpenMP. What this is trying to, this will get, again, it's kind of a hint, but it's encouraging the runtime not to deliver fewer threads than what you asked for. If OMP dynamic is set to true, then what the runtime will typically do is monitor the load on the system and try and and if all the if you're in a situation where all your cores or most of your cores are currently busy running something, then it will try not to and you ask for some threads in a parallel region or at the beginning of the program, then the implementation will try not to oversubscribe the system. Okay, so typically, but that's typically not the behavior we want. Okay, we want it really to create the number of threads we ask for. So setting OMP dynamic as false is a hint to encourage that. And the third one is to set OMP proc bind equals true. So what that does is it encourages or it really tells the OpenMP runtime that you want it to fix threads onto cores and keep them there for the duration of the application run. Okay, so to try and prevent threads migrating between cores as your application runs, because there is some cost associated with migrating threads. Again, so batch systems will typically, batch system like Slurm will typically take care of this for you, or some combination. It's very much depends on the individual setup on the machine actually. So as to there is some contention here, if you like, between what's responsible for binding and mapping processes and threads. Okay, is it the batch system, or is it the OpenMP runtime, or is it some combination? Typically, it's some combination of those. They have to be set up in a way that they will work together to do the right thing, to bind threads to cores and leave them there. Again, in a batch context, it has to bind them not to any old cores, but to the right set of cores, the right subset of cores. Okay, so yeah, talked a bit about tools. Okay, so debugging tools. So traditional debugging tools like DDT or Total View do have support for OpenMP in them. Okay, so you can do things like you can run a multi-threaded program. You can you can stop and start individual threads. You can switch between which thread you're currently viewing and all this kind of thing. So that's great, but they are not much help for tracking down race conditions. Okay, and the reason is that running under the debugger can completely change the relative timing of events on different threads. Okay, so what often happens is that you've got a race condition because you've got indeterminate, you're seeing non-deterministic behavior from your program. You run it under the debugger, and then the non-determinism goes away because the way the debugger is working is it's maybe running, it maybe only runs actually progresses one thread at a time, or things like that, or it completely changes the timing behavior so that the observable results of the race condition just go away. So what you can do is use a different type of tool, so not a traditional debugger, but a race detection tool. And these work in a completely different way. So what they do is that they instrument your code, and when your code runs, they capture all the memory, a trace of all the memory accesses that happened, and then they post-analyze that trace for data races which might, or for race conditions which might have happened. Okay, so the trace includes all the memory accesses and all the synchronization points between threads, and then it's able to post-analyze that trace and spot instances where you have unsynchronized reads and writes to shared memory. Okay, so there are a few tools that can do that. Okay, so Intel has one, There's one that's part of the Valgrind suite, and there's one that's part of that comes along with the Clang compiler packages distributions. So these are again, with all tools, they have quite a bit of a learning curve. You have to invest a certain amount of time learning how to use them and how to interpret the results that they produce. And they are sometimes prone to false positives as well. They can throw up race conditions which aren't actually aren't really a problem. But that's at least it's definitely better than nothing. They're useful for trying to track down race conditions. So again, you also have to typically, running a full application can produce an awful lot of trace data. So you might have to quite carefully choose your problem size, reduce your problem size to something that's manageable in order to get the tool to work. Okay, and the last of all is timers. Yeah, again, I sort of mentioned this before, but if you're timing multi-threaded code, then make sure your timer does actually measure wall clock time. Okay, because otherwise it's very confusing. So definitely OMP get W time is a good one to use. So don't use Linux clock function, for example. What that does is it doesn't measure wall clock time. It measures the CPU time accumulated across all the threads. So you say, okay, measure the clock. No wonder you never see any speed up, okay, because the accumulated CPU time is at best it's going to remain constant, and in most cases it'll actually increase as you increase the number of threads. So that's a trap to avoid. Okay, anybody have any questions? Okay, if not, then we'll take a break and we'll resume in half an hour. So let's say five past 11. Okay, welcome back, everybody. So this is the last lecture of the course, because Thursday's session will be me talking through the solutions to or potential solutions to the practical exercises. So this is the last piece of the last bit of lecture material. So in this one, I'm going to focus on performance issues. Okay. So I hope you've seen, well, writing OpenMP is not too difficult. Writing correct OpenMP is a little bit more difficult, but you can very quickly end up in a scenario like this. Okay, so you wrote your OpenMP program, and you've checked that it gives you the right answers, and then okay, I go run some benchmarking tests, run some timing tests, and the speed that I got, well, it's really quite disappointing. So now what do you do? Okay, so most of us probably been here, or if you're new to MP or new to OpenMP, then you will be here sooner or later. So what happened to your performance? Where did it go? So the way I like to think of it is that it disappeared into overheads of one sort or another. Okay, and so the way that I like to think about performance issues is to try and think about classifying performance problems into different sources of overhead. Okay. And there are basically 6 main ones that I'm going to talk about. So these are the and another sort of minor one. So these are the 6.5 evil things that can spoil the performance of your OpenMP code. So there are sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention are the main 6. And the minor one is compiler non-optimization. So we're going to take a look at each of those in turn and discuss ways of things we can do to avoid them or reduce them. And some of them are relatively easy and straightforward to think about. Some of them are more complicated and difficult. So let's start off with one of the easier ones, which is sequential code. Okay, so in OpenMP, because of the fork join parallelism model, all the code outside parallel regions is sequential code. Okay, and so is code inside master or single directives effectively sequential as well, mostly. So this means that the execution time spent in sequential code is going to limit the performance gains that we can have. That's just a simple example of Amdahl's law in action. Okay, so for example, if I have a program and the code that accounts for 20% of the original execution time is not parallelized, it stays sequential, I can never get more than 5 times speed up. Okay, so no matter how hard I try, that 20% will not change. So there's no way I can get more than 5 times speed up. So if that's the problem, then it's basically a question of, well, we haven't finished the job. Okay, so we need to think about, what are the remaining important contributors to execution time from the code. What can we do to try and parallelize those? So it's really, this is okay. We've parallelized some of the important parts of the code, but not enough. So we're going to have to keep going and try and do more parallelization. Okay. Next one is idle threads. So this typically happens where some threads finish a piece of computation before others and have to wait for others to catch up at some synchronization point. So a very common situation we have in OpenMP is threads sitting idle in a barrier at the end of a parallel loop or a parallel region. Okay, the execution time for different threads isn't the same. So when we reach a barrier, some threads have to sit there and wait for the last thread to arrive. Okay, so this kind of illustration was a kind of sort of schematic activity diagram here. So suppose I have 4 threads and time runs from left to right. And so the blue stuff is supposed to indicate the threads where the threads are doing useful computation, and the red bit is where they're waiting idle. Okay, so these 4 threads have different amounts of computation to do, and then there's a barrier synchronization at the end of the loop or the end of the parallel region. So these 3 threads with the red bits have to sit there waiting for the 3rd thread, which is taking the longest time to show up at the barrier. Okay. So those red bits are idle time, threads doing nothing useful, so that contributes to overhead and lack of speed up. So what can we do to avoid load imbalance? Well, if it's a parallel loop, then clearly we can experiment with the different schedule kinds and chunk sizes, and use the runtime option to avoid recompiling while we're experimenting. I haven't talked about tasks, OpenMP tasks in this course. That comes in the that's included in the advanced OpenMP course that we run as part of the ARCHER2 training program. But for more irregular computations, using tasks can be helpful because the runtime is then supposed to take care of the load balancing for us. Okay. So of course it's as you can imagine, it's not that straight. It's not as simple as that, but it can be useful. But that's kind of a topic for a different course. Important thing to keep in mind is that it's not always safe to assume that two threads doing the same number of computations will actually take the same amount of time to do it. Why is that? Well, because the time taken to load and store data may be different between the different threads, because that might depend on if or where that data is cached. So although you have two threads, they're executing the same code, or they're doing the same amount of computation, the same number of floating point operations, for example, same number of loop iterations, it's not always safe to assume that those two threads are going to actually take the same amount of time. So that's something that's worth bearing in mind. That can be the differences in time taken to load and store data from memory can cause load imbalance. Okay, so there can be other situations where we can get idle threads. So another common example in OpenMP might be critical sections. So threads can be idle, waiting to access a critical section. So that could be a critical region in OpenMP, or atomics, or lock routines. So anything that enforces mutual exclusion. So in this case, so my activity diagram has the critical section is represented by the green stripy bit of time. So this is supposed to be represent a critical section which only one thread at a time can enter. So even if the threads all show up at the critical section at the same time, they have to take turns executing it. So that means that some of the threads will be idle for a certain amount of time, waiting to access the critical section. So what can we do? Well, you can think about, we can try to minimize the time spent in the critical section and try and optimize that code from a sequential optimization point of view, or try to cut it down to the minimum amount of code that's actually needed for correctness. Okay, so OpenMP critical regions are really a global lock. Okay, I didn't mention this, but it is possible to use critical directives with different names to protect different data structures. But it's kind of the reason I don't mention it is that it's kind of clunky and awkward and doesn't scale very well. You should use atomics if possible. Okay, if it's a situation that admits atomics, then you should try and use them. It allows more optimization, so in particular concurrent updates to different array elements. Or you could use multiple locks. Okay, if you're trying to protect different data structures or different parts of a data structure separately, then you might want to use multiple locks to do that. say, atomics generally have lower overhead. The overhead of acquiring and releasing a lock and entering and exiting a critical region are usually roughly about the same, because the critical regions are using the locks underneath. Okay, so they might not directly call the OpenMP locks, but both critical regions and locks will be implemented using the same underlying mechanism typically. Okay, any questions about that so far? Okay, so we've got sequential code, idle threads. The next one is synchronization. So every time we synchronize threads, there's going to be some overhead, even if the threads are never idle. Okay, so even if all the threads arrive at the end of a parallel loop or end of a parallel region or at an explicit barrier at exactly the same time, actually getting through the barrier itself takes some time, because the threads have to communicate with each other somehow, and they're doing that via accesses to the memory system. Okay, so all synchronization is implemented at some low level via reads and writes to, and possibly special types of reads and writes to memory locations underneath. And the way OpenMP is designed is that many OpenMP codes are really full of these implicit barriers. So at the end of parallel regions and parallel loops, we always have this implicit barrier by default. And barriers can be expensive. So earlier today, I talked about the overhead of parallel regions of being order of microseconds, tens of microseconds. Most of that cost comes from the barrier at the end. So again, it depends on the cost depends on the number of threads, depends on the implementation, depends on the hardware that you're running on. But say, so thousands to tens of thousands of clock cycles. So on modern hardware, that translates to the order of microseconds or tens of microseconds. And also the other synchronization mechanisms are not free either. Okay, they're not as expensive as barriers, but every time we acquire and release a lock or use an atomic or go in and out of critical regions, there's some overhead occurred there, even if the thread goes straight into the critical section, for example. Even if it doesn't have to wait, just the action of entering and exiting the critical section, which requires acquiring and releasing an underlying lock, for example. So that's not free either. And again, I haven't talked about tasks, but creating and executing tasks also requires some synchronization to happen. Okay. What can we do to try and avoid synchronization overheads? Well, one thing we can think about as a general principle is to try and parallelize our code or our algorithm at the outermost level possible. So to try to have large, long-running pieces of execution for each thread to do between the points where they need to synchronize. Okay, so we want to try and minimize the frequency of barriers being executed. And so that might require reordering loops and potentially also reordering array indices, for example. So it can be quite that's not necessarily a trivial change to the sequential code. Okay. So you can think about using no wait clauses, but again, being very careful to avoid race conditions and using atomics. Okay, so kind of qualified that here. Atomics might have less overhead than criticals and locks. In most current implementations of OpenMP, that is true. So it's not guaranteed by the specification, but most implementations these days do a good job of optimizing atomics. Okay, so the next possible cause of overheads is scheduling. Okay. So whenever we create computational tasks in OpenMP and we rely on the runtime to assign those tasks to threads, okay, so when we're using parts of OpenMP where we don't specify which thread is going to do what, we're just saying what's parallel, and we're allowing the runtime to decide which thread executes which piece of computation, then we incur some overheads. And okay, so some of that is actually going to be internal synchronization in the runtime. But that's, so there is some kind of, it's not quite independent from the synchronization, but it's kind of implicit synchronization that has to go on underneath. So it's useful to think about it as a category in its own right. So things in particular like the non-static loop schedules are ways of specifying what's parallel, but relying on the OpenMP runtime to actually decide which pieces of computation are going to be executed by which threads in some dynamic fashion. Writing code like this, okay, so we've got a loop which can, which has a very large number of iterations where maybe each iteration doesn't do very much work, then using something like scheduled dynamic 1, where every single loop iteration is considered a task or a work item to be scheduled to different threads, then that's probably not going to end out very well, okay? So you can easily end up with the scheduling overheads costing you quite a lot here. So really, this is a question of getting the granularity of our computational tasks right. Okay, if we have too few big tasks, then we might not succeed in getting good load balance. So that might result us in having idle threads. On the other hand, if we have lots and lots of very small or quick running tasks, then we can end up with good load balance, but incurring heavy scheduling overheads. So there's often useful to think about, okay, there is probably going to be some range of granularity in the middle where performance is optimized, where we can get good load balance, but not excessive scheduling overheads. And finding that and encoding that in our application may not always be that easy, okay? Because the granularity can depend on the input to the code. Okay. Any questions on that bit? Okay, so the next topic is probably the most difficult one. It's difficult to understand. Also, it's conceptually difficult and also difficult to deal with, difficult to diagnose. So this is when we have communication between threads. So on shared memory systems, communication in some senses is disguised. Okay, it's not there explicitly. But what's happening is that we're incurring some increased memory access costs. That's because it takes longer to access data that's in main memory, or data that's in another processor's cache than it does to get it from a local cache. You know, and have to remember that on modern hardware, memory accesses are expensive. You know, it takes order of 100 or maybe, you know, a couple of hundred clock cycles to get a piece of data from main memory into the core, you know, compared to a handful of cycles, you know, maybe sort of 1, 2, 3 cycles to do a floating point operation. So you know, memory accesses are kind of, so 2 orders of magnitude more expensive than arithmetic. And communication between processors or between cores in shared memory system takes place via the cache coherency mechanism. Okay, and I'm going to give a very brief overview of how that works in a moment. And in contrast to message passing, in shared memory programs, then we have a problem because communication is very fine-grained. Okay? So it's at the level of individual loads and stores, and it's also spread throughout the program in a way that's hard to see. So if you've written any MPI programs, then any communication is, well, it's easy to spot, okay? So the only way that MPI programs communicate is when you call the MPI library, whether that's point-to-point communication or collective communication, okay? So you can look at an MPI code and you can immediately tell where the communication is happening because it has to be inside calls to the MPI library. If you look at a OpenMP code and ask where is communication happening, that's much more difficult to spot because it's just the cost of different memory accesses. So you know, a given memory access may or may not involve some amount of communication between threads. So you can't easily detect it just by eyeballing the code. And the fine-grainedness also means that it's much harder for tools to monitor it for you. Okay? So it's relatively easy for profiling tools to instrument the MPI library and record how much time every communication takes, and and exactly where it came from in the code, and report that to you in a nice way. For multi-threaded programs, for shared memory programs, it's much harder because, again, the communication is happening on the granularity of individual memory accesses. So trying to get a tool to monitor every memory access without excessive overheads is really difficult. So it's quite hard to get tools. We'll talk a little bit about performance analysis tools at the end of this session. But communication costs is one thing that performance analysis tools really typically don't handle very well. There's not very much they can directly tell you about them. Okay, so cache coherency in a nutshell, or in a single slide. Okay, so this is the details of cache coherency mechanisms are extremely complicated, but you don't really need to know. Okay, you just need a fairly you need a very high level mental picture of what's going on, and you don't need to know the gory details. And in fact, most of the gory details are generally proprietary, so you can't even find them out if you want to anyway. Okay, so the way this works, okay, so imagine if you think about a picture of our shared memory system, or shared memory hardware. We're running threads across multiple cores, and each core has some local cache memory associated with it. Okay, which is dedicated to that core. Okay, so again, the cache hierarchy in modern systems is complicated. You typically have a level 1 and a level 2 cache for every core, and then you have a level 3 cache which is shared between some number of cores, maybe all the cores in a chip, maybe not, depending on the CPU design. So again, details are complicated, but again, we don't need to consider that too much. Okay. So the problem that the hardware is trying to solve here is, despite all the fact that there may be many copies of a particular memory address, the actual values of a memory location in all these different caches, the hardware has to maintain an illusion for us as a programmer as though there's only one copy. Okay, and so the way it does this is called the cache coherency mechanism. And so the high-level view of how it works is that whenever a thread writes a data item, it will get an exclusive copy of that data in its local cache. So every time a piece of data is modified, the processor or the core that wrote it will get will take exclusive ownership of that data item in its local cache. And any other copies of that data item in any other caches will be marked as invalid, so that other cores are not able to read any out-of-date values. So those copies will still exist in other caches, but they'll be marked as being out of date, so that they can't be, so that the data values can't be used. And then what happens is that subsequent accesses to that data item by other threads running on other cores will have to get the data from wherever the exclusive copy is. Okay, and that takes time because that requires moving data in the hardware from one cache to another cache. So that's the high-level view. As I said, it's a very highly simplified description of what's going on, but that's sufficient mental picture for us for almost all what we need to do to reason about what's happening in our programs. So one thing we do need, because of this mechanism, one thing we need to think about is data affinity, because data is going to get cached on the processors which are accessing it, so we have to reuse that cached data as much as possible. So what does that mean in practice? We need to try to write code with good data affinity. What does that mean? Means we try to ensure that the same thread accesses the same subset of program data as much as possible. Okay. So one of the things that makes shared memory programming easier than message passing program is that we don't have to do any explicit data distribution. We don't have to do data decomposition. But nevertheless, for performance reasons, we still have to think about data decomposition, at least for some, for the computational intense part of the program, to try and make sure that different threads always access the same subset of program data, which means that the threads don't need to communicate very much with each other, to try and minimize the amount of communication that happens. And for reasons I'll come on to in a minute, we have to try and make those subsets should be reasonably large and contiguous. Okay, so having very fine interleaving of data accesses between different threads can be bad, and I'll explain why in a moment. This is also why it's important to prevent threads from migrating between cores while the code is running. Okay, so think about what's happening. So a thread is running on a particular core. It's accessing some data. It's getting copies of that data in its local cache, which it can access quickly. If the operating system then decides to migrate that thread to a different core, then it'll be in a situation where all that data is now in the wrong place. Okay, and the cache coherency mechanism will kind of migrate that data across to the caches where the thread has moved to, but there's some overhead in doing that. Okay, there's a bunch of remote memory accesses or remote cache accesses that have to take place every time we move a thread from one core to another. So basically, we don't want that to happen. So we can either use the OpenMP mechanisms like OMP proc bind, or more typically in HPC systems, we're using the batch system settings to ensure that our threads are bound to cores and that they don't move around. Okay, so here's an example of where data affinity matters or might matter. Okay. So, okay, slightly complicated example, so I'll talk through it fairly carefully here. So I've got two parallel loops here, and to begin with, I want to focus on the second one here. Okay, so this loop reads some values from this two-dimensional array A. Okay, and it's a doubly nested loop over I and J, and to look at the bounds of the J loop. So J runs from 0 up to J less than I, okay, where I is the iterator for the outer loop. Okay, so this is a triangular loop nest. So that means that if we parallelize, if we use OMP parallel 4 on the outermost loop, then that won't be well balanced, okay, because small values of I have fewer iterations of the inner loop. So we might consider, if we just considered this loop in isolation, we might say, okay, so we need to, it's not naturally well balanced, so we need to choose a suitable schedule for it. Okay, so maybe we do some experiments and we find that, okay, static schedule with a chunk size of 16, for example, turns out to be a reasonable solution for this loop. But then if we look back to the previous loop, which is where this array A was last written, then this loop nest has a different structure. This is a rectangular loop nest. So instead of J equals 0 up to J less than I, we've got J less than N here. So this is writing the entire array, whereas this is only accessing so one half of the rectangle, if you like. So one of the triangles. So again, on the face of it, this looks like a well load balanced loop because every I iteration contains the same amount of work. Every I iteration contains the same number of J iterations. So you might think, okay, for this loop, it's balanced, so we can just use schedule static. But then think about what's happening to these accesses to A. So we are dividing up the I loop. So different parts of this array A will end up in different caches. Okay, so these writes will occur. We'll get exclusive copies of parts of A in different caches. But then, because this loop schedule is different down here, for most of the values in AIJ, the thread that reads AIJ in this loop is not the same thread that wrote it here. So most of these accesses will incur these cache coherency operations to retrieve the value of AIJ from the caches attached to some remote core. So patterns like this will result in a lot of communication. So in this example, then there's an obvious solution. We might decide, okay, let's apply the same schedule, static 16, to this loop as well. And then we get a match between the access patterns to A in this loop, and then the accesses to AIJ will all be to the same all come from the same thread as they did here, and so the data affinity should be much better. Okay, so another example, so just to give you an idea of other patterns where we can get bad data affinity. Again, so suppose we have a parallel loop that does read accesses to some array A, and then we have a sequential loop which writes some new values into A, and then we repeat the parallel loop that reads it again. So again, the way the cache coherency mechanism works here means that this will have bad data affinity, okay? Because we execute this loop, even though we're reading, we will get copies of parts of A spread across different caches. This sequential write will invalidate all those copies and we'll end up with exclusive copies of the elements of A in one cache. And then when we come to read them again, all those accesses have to go to that one cache to get the updated values. So even though, we might think, you might do some initial profiling of our code, tells us that this, maybe this code doesn't really take very much time, so we didn't bother to parallelize this code. And that might be true, but nevertheless, because of this access pattern, we're going to induce a bunch of communication between threads on these elements of A, and cause some overheads because of that. So something strange that you could observe here potentially is that if you measured the time for this sequential loop, it would get slower when we executed the parallel loops with more threads. Okay, so compared to executing the whole code sequentially, when we execute these loops in parallel, this bad data access pattern means that these invalidations operations have to happen in this loop, which wouldn't have had to happen in the sequential code. So this sequential code will take longer when we execute in parallel with multiple threads, which is a bit strange. Okay, yeah, so I've said most of this probably. So yeah, sequential code can take longer because of the cache invalidations, and the second parallel region is going to scale badly because it's we're having additional cache misses to retrieve the new values. Okay. So this is a case where you may need to for data affinity reasons, you might need to parallelize code which appears not to take much time in the sequential program. Okay. So in this case, you might want to parallelize this, but you might be able to do even better. You might be able to say, merge these two loops together into a single loop and parallelize and have them both executing in parallel, and that'll improve the cache utilization from a sequential point of view as well. So that would generally be a good idea if that was possible. Okay. So that's bad, but it gets worse. So the next consideration we might need to think about is what are called NUMA effects. So NUMA stands for non-uniform memory access. Okay, and so the issue here is that on a lot of modern chips, and certainly if we have like most supercomputer setups, if we have more than one chip in a node. So again, just remember that systems like ARCHER2, there are 2 chips consisting in each node. Okay, so chip, socket, same terminology. Okay, we've got two two sockets, each containing a separate chip. So an ARCHER2 got two AMD Rome chips in the node, each of which has 64 cores in it. So basically, all current multi-socket 86 systems have this non-uniform memory access design where some subset of cores, so that might be the whole chip or it might be part of a chip, has its own part of main memory associated with it. So that means that where data is actually located in main memory is important for performance reasons. And OpenMP doesn't have any direct support for controlling this. So you don't have a way of specifying via OpenMP directly where your program variables are actually going to be stored in the different bits of main memory. So on ARCHER2, the AMD Rome processors, each chip actually has 4 separate NUMA domains. So that means that every subset of 16 cores has its own physical piece of main memory associated with it. So even though every core can access all the memory in the node, it's not uniform memory. It's not uniform cost. Okay, so it's cheaper to access the local memory to those 16 cores than it is to access the rest of the memory in the node. Who's responsible for placing the data? Okay, so where do your program variables actually get stored in main memory? That's the responsibility of the operating system. And common default policy for certainly for Linux, which is kind of everywhere these days, is for the operating system to place data, on the processor or close to the cores which first accesses it. So this is what's called a first touch policy. So depending on which core accesses that is the first one to make an access to that piece of data. And this is done on a page basis, so this is typically 4 kilobytes or 4, 8, 16 kilobyte chunks of data. So whichever core makes the first access to that page of data, that's where it will get, or the local main memory for that core is where that page of data will get stored. And it'll stay there for the whole duration of the application. Okay, so most systems don't move. Once they've allocated a page into main memory, it stays there forever and until the application finishes. So for a lot of applications, that's a good choice, because provided the application carries on running on the core, then its memory is located locally. And so that works fine if we have single process applications. It also works fine for MPI applications where every MPI process has its own data. So that's also a good choice. However, for OpenMP programs, it can be the worst possible thing to do. Because what can happen is that if our data initialization happens in the sequential part of the OpenMP program, then all of that data gets allocated. All of our program data, if it will fit, will be allocated in one of these sockets or NUMA domains. And then having all our threads trying to access the data that belongs in the same chunk of main memory becomes a bottleneck. So effectively what we end up doing is we end up effectively reducing the available memory bandwidth for our application. And a lot of HPC applications are limited by memory bandwidth rather than by computation. So what can we do? Well, some operating systems we can change the default behavior from first touch. So in Linux, you can do things. There's a command called numactl, which you can use to change the policy for that particular process to from first touch to something different, like round robin, where it just spreads the pages around across all the different NUMA regions. That's okay. It's a bit crude, but it's better than nothing. What we can do though is to basically recognize that there is a first touch policy and use that to control our data placement indirectly by parallelizing our data initialization. Okay, so that might seem completely not worthwhile in view of the insignificant time that our initialization takes in the sequential code. You might have a program which takes a couple of seconds to initialize all its data structures and then runs for hours. So why would you bother parallelizing that initialization bit of the code? But it's that part which is going to determine where that data is going to live for the entire duration of the program. So it might well be worth trying to parallelize that and to try and get your data distribution. You don't have to get the distribution exactly right necessarily, and exactly what the right distribution is may not be completely obvious. But at least avoiding this situation where all your data is in one NUMA region is at least a good thing to do. And again, how easy is it to parallelize your data initialization? Well, it depends on the nature of the data structures in your program. If your main data structures are large multidimensional arrays, which is quite a common case in scientific computations, then it's pretty easy. Okay, you can just put you can just stick a parallel loop around the data initialization. That does the job for you. If it's more complicated data structures, if you're building trees or graphs which grow organically as the program evolves, data structures where things are continuously being added and deleted and so on, then it can be much more difficult. So just have to remember when you're doing this and you're thinking about doing this, that the allocation is on an operating system page basis. Okay, so this is typically by default, it's of the order of kilobytes. This is the size of the pages. Okay. Sometimes you have an option to increase the page size. That has, in some situations, that has performance benefits, but it would make it harder to do this effectively. If you have very large pages, then it makes it more difficult to get the data distributed across different NUMA regions. Okay, so it's a problem. In terms of running codes on ARCHER2, most of the time we're thinking about running OpenMP codes. We're not thinking about standalone OpenMP. We're thinking about hybrid MPI plus OpenMP code. And in that case, that's a reason why we would normally restrict the number of threads to be such that we have at least one MPI process per NUMA region. So you'd want to run at least 8 MPI processes per node on ARCHER2 and not use more than 16 threads per process. And that makes sure that if you do that, then that ensures that you don't run into this problem. And as soon as you start using more than 16 threads per process, then you have to start worrying about this. And unless you take care of it, probably what you'll find is that the performance will be significantly worse. Okay, again, something else which is not obvious and very unpleasant, though to be fair, modern hardware designs have gone some way to mitigating these issues. It's not as bad as it used to be on on earlier chip designs, which is good. But nevertheless, it's still potentially a problem. And this problem is called false sharing, and it happens because the units of data on which the cache coherency operations are done, okay, so these getting exclusive copies and invalidating other copies in other caches, all this cache coherency mechanism operates on chunks of data which are bigger than a word, okay, so it all operates on cache blocks or cache lines, and the size of those is typically something like 64 or 128 bytes of data. So that's bigger than an individual word, okay? So an individual integer or floating point value will typically occupy 4 or 8 bytes. So that means we can run into the situation where we have a program where logically there's no race conditions, logically no communication should be happening, but if different threads write to neighboring words in memory, then we can still cause cache invalidations to happen. Okay, and it's still a problem even if we just have one thread writing and others reading. If all the threads are just reading, then we don't have a problem. Okay, every cache will get its own copy. There's the data's not changing, so there's no need to get exclusive copies. There's no need for invalidations to happen. Every cache can just every thread can just carry on reading the data from its own locally cached copy, and if the value is not changing, that's fine. But as soon as one of the threads is changing the values, then that will cause invalidations to happen, even though the other threads are not reading the same data value. They're not reading the same word. They just happen to be reading different words that are near enough to the thing that's being written in order for them to lie on the same cache line. Okay, so typically, I say this modern hardware has gone some way to, modern cache designs have gone some way to reduce the effects of this. But the worst situations and the things that you should think of, worry about are where different threads are doing lots of writes to neighboring array elements. Okay, so if I, for example, if I want a data structure if I have a shared array in my program called count, okay, so I want to count something for every thread, but I don't want it to be a private variable because reasons, because I want every thread to be able to see the values at some point. Then, so if I, for example, if I use my thread ID to index this array and do and increment the value very often, then that's a pattern which would potentially trigger this false sharing problem. And you can also run into it in cases like this. Okay, so again, this is one of these triangular loop nests where I want to use choose a schedule clause to get load balance. So in this case, if I used a static 1 schedule for the I loop, that would mean that different threads would be reading and writing to the elements of B. Okay, so that again, that's another pattern that could trigger this problem. And so that's one reason why if you experiment with different chunk sizes, you might well find that small values are bad, okay, because it's triggering this problem. So that's one reason why choosing a chunk size of 1 is not necessarily optimal, because it can result in this kind of problem. Phew, so that's communication. As I say, it's a difficult thing to reason about. It's a difficult thing to detect. So it's difficult to get tools to think of, to worry about it. And it's kind of the sort of it's the thing that you suspect that you try and eliminate all other causes of bad performance first, okay, which are easier to detect. And then if you're still left with bad speed up, then you have to think about, okay, it's probably due to communication and these kind of memory effects. Okay, so so we've done 5 out of the 6 so far. So the last one is hardware resource contention. So the way shared memory hardware is designed is there's some cost performance trade-offs going on, and there are shared resources which, if all the cores try to access them at the same time, don't scale. Or you can look at it the other way around. You know, this is one of these sort of, you know, glass half full, glass half empty conundrums. If you want the glass half full point of view, is that, you know, an application that's running on a single core gets access to more than its fair share, more than one core's worth of the resources on the chip or on the node. But in particular, you know, cores and therefore the OpenMP threads which are running them can contend for memory bandwidth is probably the most important one, but also for cache capacity. Okay, so caches have a limited size. For shared caches, for level 3 cache, then, you know, we have threads competing to store data in the same level 3 cache. And we can also contend for functional units like floating point units if we use simultaneous multi-threading. So if we use hardware threads where we try to run more than one thread per core, then we can also run into problems there with contention, okay? Because the core has, you know, only one set of floating point units, which are shared by, say, typically there's two hardware threads, so which are shared by both the hardware threads, so they can't both use them at the same time. Okay, so memory bandwidth is probably the big deal. So codes which are very bandwidth hungry or even modestly bandwidth hungry are not going to scale linearly on most shared memory hardware. Okay, so even if you run a very simple program, which all it does is access memory a lot, okay, does virtually no computation, then, you know, parallelizing that with doesn't matter. You know, if you parallelize that with OpenMP, with MPI, as long as you test the scalability with increasing numbers of cores inside a single node, you're not going to see good scaling. What can you do about this? Well, you know, this is just about trying to reduce the bandwidth demands by improving the locality of your code and trying to reuse data that's in caches as much as possible. That's an optimization technique that's going to benefit your sequential performance as well, but it's, you know, it's kind of double the effect with when you have every core hammering the memory bandwidth. Okay, so I didn't want to spam you with too much data, you know, actual real data, but I think this is a nice illustration for excuse me, for what can go on with and just how bad this problem is. Okay, so this experiment was done on ARCHER2. So this is on a single node, in fact, on a single chip, which is AMD ROMs. Okay, and as I say, we have one NUMA region is attached to 16 cores. Okay, so all these experiments are done in a single NUMA region. So there's no, so all the cores have access to are accessing the same chunk of main memory. So each core has its own level 1 and level 2 caches. And then there's the way the level 3 cache is structured on ARCHER2 is that there is 16 megabytes of shared L3 cache for every set of 4 cores. And so it's a slightly unusual hardware design in that respect. Okay, so what I'm going to do is take this very simple parallel loop with OpenMP. Okay, the fact that it's doing reduction doesn't really matter, but the point is that basically this is, so almost all the cost of executing this loop is actually loading the values of the array A from memory. Okay, so the amount of time doing the additions and the reduction at the end is almost negligible. Okay, so all the cost of doing something like this, say because of this 2 orders of magnitude imbalance between arithmetic costs and memory access costs, almost all the expense of executing this piece of code comes from the memory accesses and not from the arithmetic. Okay, so what I'm going to do is run this for different values of n, and different numbers of threads, and calculate for different values of n, calculate how much speed up I get from this. Okay, and it looks like a nice simple piece of code. It's all well load balanced, but as we'll see, it's almost impossible to get this code to scale well. Okay, so it's a graph which takes, I need to explain this a little bit. Okay, so what I'm doing for this, so look at this loop. Okay, so number of loop iterations is n. Okay, so that's what's being plotted along the horizontal axis here. Okay, so starting at 1,000 and going up to 100 million loop iterations. Okay. So I'm going to run that on different numbers of threads and calculate the speed up that I get compared to running it on a single thread. Okay, so I have I get a line on the plot for every different number of threads. Okay, so we've got a line for 2, 4, 8, and 16 threads. Okay, so what can we see here? Well, first of all, for small values of n, then we see that the speed up is much less than 1. So that means that the parallel code is much slower than the sequential code. And what's happening here is effectively death by synchronization. Okay, so the overhead of this is effectively the overhead of the barrier synchronization at the end of the parallel region is completely overwhelming any benefit of the parallelization. Okay. So depending on the number of threads, okay, it turns out that we need 50,000, 100,000, 200,000 iterations just to get to a speed up of 1. Okay, so just to recover just to get back to the one-threaded performance. So I mean that's partly a reflection of how well the compiler does in optimizing that code. Okay, so it vectorizes nicely. It's so it generates vectorized loads and stores, vectorized additions. So it generates very efficient assembly code. But that means that the number of iterations that I need to overcome the cost of the barrier synchronization is a lot. Okay, so let's look at 2 threads first. So that's the light blue line here. So once we've overcome the synchronization cost, I reach a speed up of 2 on 2 threads, which is kind of what I'd like, what I'd expect. Can't really hope for much more than that. And that stays constant for pretty much regardless of how big the loop gets. So that's nice. Okay, straightforward to explain. We go to 4 threads, which is the orange curve here. Well, eventually I do get up to a speed up of 4. But then as the loop gets longer and consequently the array, the amount of data in the array gets bigger, the performance drops a bit. The speed up drops to around 3 and a bit. And then eventually it drops again back down to about 2. So what's going on here? Okay, so once we get to this size of data here, then the data fits in the level 3 cache. But we are now contending that we've got 4 cores all trying to access data from the level 3 cache. And the bandwidth between the level 3 cache and the cores doesn't scale perfectly. So that means that we don't get 4 times speed up in here. And once we go beyond this point, what's happening is the data no longer fits in the level 3 cache. It comes from, so this is plot from data. This is real data, okay? So could you model it? You could model it for very simple loops like this, okay? For trying to model it for real application codes would be very difficult, because trying to figure out where you get cache misses in general is hard. Okay, so you could potentially predict this for for a simple case, but for real codes probably not. Okay, so once our data gets big enough, doesn't fit in level 3 cache anymore, all the memory accesses have to come from main memory, and now the speed up drops to 2. Okay, so even though we've only got 4 threads running, the main memory bandwidth just isn't scaling at all here. Okay, with 8 threads, we see something a bit strange happening. Okay, so we initially get some increases. We don't reach 8 times speed up. The performance drops for a bit, but then we get a sudden spike, and we can end up with a particular data size where we practically get 16 times speed up on 8 threads. So that looks weird. How can that happen? Well, it happens because at this particular data size, the data doesn't fit in one level 3 cache, but it does fit in 2 level 3 caches. And so we're running 8 threads on 8 cores. So compared to for 1 thread, we now have twice as much of level 3 cache available. 1 thread can only access one of these 16 megabyte caches. 8 threads, we are using 2 level 3 caches. So we double the amount of level 3 cache available, which is why we can end up with this strange behavior where we end up with speed up which is greater than the number of threads. Okay, but then as soon as we exceed the capacity of two level 3 caches, then the speed up crashes back down, okay, to just over 2. Okay, and the same thing happens for 16 threads. The peak is a bit wider now because now we have access to 4 level 3 caches, because we've now got 16 threads running on 16 cores and 4 level caches. But after this, if our data is big enough such that all the accesses come from main memory, then the scalability is really, really bad. Okay, we never get more than about 2.5 times speed up, even with 16 threads. And this is because these threads are all contending for, and the performance here is entirely dependent on the memory bandwidth. So the AMD ROMs are particular for this chip. This effect is particularly pronounced. Okay, other chips don't have quite such a pronounced effect. But you still, if you're in this, but nevertheless, if you're operating in this regime, you're never ever going to get speed up equal to the number of threads, because you will just be contending for memory bandwidth. Okay, so other things we can contend with is, cache space. Okay, so if we're sharing some level of cache, then codes can appear not to scale well, because what often happens if we run on a single core, then we have access to the whole of that shared cache. Whereas if we run multiple threads on multiple cores, then they have to share that cache capacity. So each thread gets access to less of the cache. So one optimization you can do for cache utilization is something called blocking. Okay, so where you structure your loops in such a way that that you try and reuse the same block of data as much as possible, and you try to match the size of those blocks to the cache. Then you have to be careful about doing that tuning on the single thread and then running multi-threaded code, because effectively you've tuned for the wrong size of cache. Hardware threads, yeah, okay, so if you use hardware threads, then OpenMP threads running on the same core, they're going to contend for functional units as well as for cache space. Okay, so now this will not only be the level 3 cache, multiple threads running on the same core, they're going to contend for level 1 and level 2 cache space as well, and for memory bandwidth. So this is one reason why using hardware threads often doesn't benefit scientific codes, because they're either floating point hungry or they're memory bandwidth hungry. So running additional using the hardware threads doesn't help. And the case where using hardware, the sort of use case where hardware threads do help, are codes where threads tend to be idle because they're waiting on memory references to happen. So this tends to be codes with non-contiguous or kind of pseudo-random looking memory access patterns are the sort of corner case where hardware threads might be beneficial. But such cases are relatively unusual. So that's why most systems like ARCHER2 disable use of hardware threads by default, and you have to do something special to ask Slurm to give you access to using hardware threads. Okay. The main problem is that typically what you need to do, in order to exploit hardware threads, you need to, if you've got 2 hardware threads per core, then in order to exploit that, you're going to have to either double the number of OpenMP threads or double the number of MPI processes, and the additional overheads that come from doing that, from communication or synchronization or load imbalance, the overhead of increasing the amount of parallelism in your application usually outweighs any benefit that you're going to get from using the hardware threads. So there are some applications where it helps a bit, but for most applications it doesn't. And finally, another instance of hardware resource contention is if we try to oversubscribe. Okay, if we try to run more threads than we have hardware execution units, so be that cores or hardware threads, is generally a bad idea. Because what has to happen in that case is your program will still run, but the operating system then tries to give each thread a fair share of access to the execution units. So it's going to be constantly swapping threads in and out, and the cost of stopping a thread and starting another one is quite high. It's order of thousands of clock cycles, and it also ruins your data locality, as we've discussed as well. So so batch systems will typically try to prevent you from doing this, but with OpenMP, then it's difficult, because you can change the number of threads that you ask for at any point inside the code, and the batch system knows nothing about that. So you can suddenly decide to ask for 500 threads inside your code, and the OpenMP runtime will happily create 500 threads for you, but then the operating system has to try to schedule those on the available cores, and it basically can't prevent you from. It's not going to prevent you from doing that, but the performance consequences are likely to be pretty terrible. Okay, so that's us gone through the 6 main causes of loss of performance in OpenMP programs. The last one is just something is rare, but just something to the 6.5 is rare, but it happens very occasionally. But it's worth knowing about just in case you get really unlucky. Okay, and this results from very occasionally adding OpenMP directives can affect the way the compiler performs its sequential optimization passes. Okay, so OpenMP directives can very occasionally interfere with the compiler optimizations that you're asking for when you set the optimization flag. If you're doing -02, -03, -0 fast, or whatever it is, you're encouraging the compiler to do as much sequential, to do a certain amount of sequential optimization, and occasionally OpenMP directives can interfere with that. The symptom that you'll usually see for that is that if you run the parallel code with OpenMP on a single thread, then it's slower than running the plain sequential code without any OpenMP. Okay, but when you disable OpenMP in the compiler. If that happens, you're very unlucky, and it can be really difficult to find a workaround for that. Okay, so sometimes you can, there are things, this is potentially a case where you might want to make private copies of shared data or try making local copies of variables, but it's usually triggered by some programming pattern that is slightly unusual, and the compiler makes a mess of it. So hard to predict, hard to deal with, thankfully pretty rare, but worth knowing that it can potentially happen. Okay, so that's a lot to think about, but I'm going to finish up by trying to think about, what's our strategy here? Okay, so we've got a code. If we've got a code that's giving poor speed up, and we don't know, from a priori, we don't know why. Any one of those 6 problems and subsets of those 6 problems could be the cause. So what do you do now? Well, okay, so I hope you won't take option 1. Okay, just say, okay, right, now this OpenMP thing is rubbish. Okay, and give up. Okay. How can we try to approach performance optimization in a sensible and logical way? So the way I would advocate is to try and classify and localize the sources of overhead. Okay, so what type of problem have we got? Which one of those 6 things is causing problems? Okay, and it might be more than one. And whereabouts in the code is it happening? So if we can do that, if we can identify which problem, what sort of overheads we're getting, and where they're coming from in the code, then we have a reasonable chance of being able to do something about it. And it often helps to use available tools for you to help you. Okay, so you can just use timers. You can get a lot of value out of timers. You can also do things like using hardware counters to count cache misses, that kind of thing. Difficult, okay, not easy to do, difficult to interpret the results. You can also use some profiling tools as well. Again, they may tell you about some of these sources of overheads. They're good about, might be good to tell you about sequential code or idle threads, might be less good to tell you about, say, communication or false sharing or problems like that. And then, okay, yeah, as with any optimization process, fix the problems which are responsible for the large overheads first. Okay, it's no good twiddling the small stuff if we've still got an elephant in the room. To mix my metaphors terribly. Okay, and then when you fix one problem, okay, measure again and see, okay, can we do what's the next problem we need to focus on? Okay, say a bit about profilers. So the kind of very standard profilers that you get, so things like gprof that comes with Linux, or the sort of profilers you get built into IDEs, can be pretty confusing for multi-threaded code, because what they typically do is they present you a flat profile, and what they don't tell you anything about threads. They're just going to accumulate the time spent in functions across all the threads in your program. So that's not useless information, but it's quite difficult to interpret. It's quite difficult to use that information to try and figure out what sort of overhead you've got. It can certainly help you localize it. Okay, it might tell you where your code's spending the time, which might be helpful, but trying to diagnose what sort of overhead it is can be difficult. You can get a lot of information from using timers. So if you instrument your code where you put a timer around every parallel region and also around the whole code, or at least the main computation part of the code that you're interested in, then at least you can do the localization part. You can work out, you can compute a speed up for every individual parallel region. So that'll tell you where your bad speed up is coming from. Okay, and it'll also tell you, it's also about, you can add up, okay, how much of my code is parallel, how much of my code is sequential. You can spot, you can calculate how much sequential code you've got just from using timers. Okay, so that's good. There are a bunch of performance tools out there. So what you get will depend on which HPC system you happen to be using, and what the owners or people who run that system have installed and have decided to pay for licenses for. But there's a bunch of them. There's things like Vampire. Again, don't see very much, unfortunately, because it's expensive. There's things like Intel have Intel VTune, Tau. Things we've got on ARCHER2 are ARMMap and CrayPat and Scalaska. So those are useful in various different ways. For OpenMP codes, I really like Scalaska because it quite explicitly tries to break down overheads into some of these different categories that I've talked about. So you can explicitly, it will explicitly measure idle thread time for you, for example, which the other. This one, yeah. Sorry, go ahead. Somebody want to ask a question? Okay. This last one is interesting because it does something a bit different to standard profilers. And standard profilers are basically just measuring how much time is spent in different functions in the code at some level. Okay, and then doing some post processing or all the other tools to update it for you. But say none of them tell you very much about memory accesses and communications and that kind of thing. This tool called ThreadSpotter is a little bit different because what it's actually doing is something a bit like the race detection tools, except it doesn't have to, for performance analysis, it doesn't have to record every memory accesses. It just takes a statistical sample of them, and then it kind of replays that through a memory system simulator. So that's how it's able to diagnose sort of cache and memory problems and things like false sharing, which other performance tools typically can't do. Okay, good. I'm sorry I have overrun very slightly today's session. That was quite a long one. Does anybody have any questions before we wrap up? Anyone said for forum or mainly someone to ask for help on other OpenMP problems? Usual answer: Stack Overflow. Yeah, there used to be a dedicated forum which was on the OpenMP website, but it got deprecated, unfortunately, and kind of everything got moved over to Stack Overflow. Okay, anything else for today? Okay, so thank you very much, everybody. As I say, that's the end of the taught material for the course. The session on Thursday, I will talk through the solutions to the practical exercises. So if you do get a chance to work on them before then that would be great. But even if you haven't, then you might find it helpful just to see the solutions and discuss how they work and so on. So hope to speak to you all again one more time on Thursday.